Now that we can identify the different hydrocarbons, the alkanes, the alkenes, and the alkynes, we're going to look at some properties, and we'll be especially noticing how the structure of the compound can affect its boiling point. Please note that this is not page 8 in your notes, it is page 9. The functional group chart was placed in between, but I would like to talk about the physical properties of aliphatic hydrocarbons first. So we're going to be using the alkanes as a model to represent all of the hydrocarbons. Because it doesn't matter how many double bonds or triple bonds they are, the solubility and boiling point will be following the same patterns. So let's look at the solubility first. When we look at these compounds, we see that they are hydrogen and carbon. These compounds are non-polar. So do you expect them to be soluble in water or oil? Yes, that's correct. Not surprisingly, these are soluble in oil-type substances. In other words, hydrocarbons are soluble in hydrocarbons. Nonpolar substances are soluble in nonpolar substances. Water is polar, and these compounds are not soluble in them. Later, we're going to see that some of our organic compounds are slightly polar, and because of that polarity, they may be a little bit soluble in water. We'll talk about those later. For the moment, you should understand that all hydrocarbons are insoluble in water and are soluble in organic solvents, and that they follow a general trend. The more carbon there is, the less soluble in water it is. Now, let's focus on the boiling point. We want to look at two major characteristics. One is the number of carbons present, and the second one is how those carbons are attached, what we call branching. Before we look at those factors, we want to discuss what affects the boiling point. The boiling point is affected by those intermolecular forces. In the case of hydrocarbons, we're looking at just London forces because we are looking at a collection of nonpolar substances. Recall that when boiling occurs, the two substances have to separate from each other. That means it has to break those intermolecular forces. The more forces there are, the harder it is to break, giving us a higher boiling point. So let's compare a fairly small hydrocarbon chain, let's say propane, 3 carbons long, to a longer chain, which is something like pentane, which has 5 carbons. In a container full of propane, we'll see that there are 3 interactions for every propane. They're stacked on top of each other, and we can see that there's only 3 points that they interact. In the case of pentane, we'll find that there are 5 places it can interact. More interactions makes it harder to boil. The more carbon there is, the harder it is to boil. We also know that the more carbon is present, the higher the molar mass, because the mass increases with the number of carbons and hydrogens. So we can say the relationship between molar mass and boiling point is that as the molar mass increases, so does the boiling point. To help me remember this, I do sort of a visual, and I think about the smaller particle, in this case the propane, being the size of a ping pong ball, and the larger particle, in this case the pentane, being more like a bowling ball. If I threw them in the air with the same amount of energy, you should see that the ping pong ball goes flying off easier. It's much easier to escape and therefore has a lower boiling point. Now let's look at the second trend in boiling point. Here we see that branching affects the interactions that we have. If we have what we call a straight chain hydrocarbon, it may look bent, but it is still a straight chain because it goes carbon, carbon, carbon with no branches. That will have a lot of interactions. So if I have a 5-carbon compound and it has no branches in it, it has 5 points of contact. On the other hand, if I have a branch on that chain, when they try to be in contact, that branch gets in the way. So we may only have 1 point of contact. How does that affect the boiling point? Well, the 5-carbon straight chain will have 5 interactions, so it is harder to break and has a higher boiling point. Every time I put a branch in, it makes it difficult to bond, and so it lowers the boiling point. So branching lowers the boiling point. For me, I like to think of this like a strip of Velcro. If I have Velcro and it's a long single strip, it is very hard to break that interparticle force and tear it off. On the other hand, if I have a whole bunch of little Velcro dots, they're barely touching and is much easier to break. The branched version is more like the dots The straight version is more like the long strip. So overall, we see that more branches gives you a lower boiling point. We'll return to looking at the intermolecular forces later when we talk about other classes of organic compounds. But the two general trends that we see here will always hold. More carbons, higher boiling point. More branches, lower boiling point.